Okay, great. Yeah, I'm Zhou. I'm going to discuss this a couple of techniques that we have experimented with for speaker detection from a large negative list. This work is done with in collaboration with Vijay, Gurbani and Chandra, Mouli at Vail Systems. So normally when we talk about speaker recognition, first of all, the negative list detection is a speaker recognition application that is commonly used in data center services as part of the fraud detection. So in the speaker recognition, normally it refers to speaker verification and the speaker identification. So speaker verification determines whether a test voice sample and a known speaker sample in the database belongs to the same speaker. And the speaker identification is trying to determine that which speaker in the database of a list of the known speakers matches the test voice sample. So negative list detection is very similar to speaker identification. In the database, it has a list of known fraudulent speaker samples, and that is called the negative list. So the task is to determine whether the test voice sample is spoken by a speaker in the negative list. So there are a couple of unique properties here. First, that it is focused on the detection, not identification, meaning that it only needs to determine whether the test sample matches any speaker in the negative list. It doesn't really care exactly which speaker it matches with. And also this is an open set problem because most of the callers are not fraudulent speakers. So most of the test samples will not find a match in the negative list. Both the speaker identification and the negative list detections are multi-speaker problems, and that they are commonly treated as a multiple single problem, single speaker verification problem, so that the test voice sample is compared with individual enrolled speakers in the database one by one to determine whether there's a match. And this picture shows a typical speaker recognition process. It consists of a front end on the left and a back end on the right. So in the front end, a model is used to extract a speaker embedding from the input audio samples. And then at the back end on the right, it takes the speaker embedding that is generated and compares that with an enrolled speaker embedding. And it produces a similarity score. So the higher the score, the more likely that the two embeddings belong to the same speaker. And this similarity score can be computed as simply as the dot product of the two vectors. That would be the cosine similarity. But for some of the embeddings, like the I vector and the X vectors, it is found that a statistical model, PLDA, would produce a better, would have a significant improvement on the detection accuracy. And PLDA stands for a probabilistic linear discriminant analysis. Its main purpose is to separate the intra-speaker variance from the inter-speaker variance. So in this work, we're going to be focusing on this back end, and we'll use the PLDA as the baseline method. So here, we would like to address a couple of challenges in negative list detection. The first is that it requires the computation of a large number of PLDA similarity scores. So often there are thousands of fraudulent speakers in the negative list in a call center service. So for each test samples, one has to compute thousands of PLDA similarity scores. And that is computationally expensive, and also it introduces a latency or the delay in the real-time detection. And the second challenge is that the PLDA similarity scores needs to be properly normalized. If we have a large set of test samples and we compute its similarity scores with the speaker A and then with the speaker B, then those two sets of scores may have a different distribution. But for negative list detection, it needs a single threshold for the score to determine whether there's a match. So for that reason, the scores need to be normalized to a single distribution first. And this is a common problem in the speaker recognition. So there have been many normalization methods developed, and they all use a normalization cohort, which is a large set of speaker embeddings. So in this talk, I'm going to use the terminology of speaker embedding and the vectors interchangeably. And also I will use a score as a shorthand for PLDA similarity score. So here we have a similarity score S between a test vector P and an enrolled vector E. So to normalize S, one can first compute the similarity scores between the test vector and every vectors in the normalization cohort. Then we use the distribution of that set of scores to normalize S. Similarly, we can do the same on the right by using the similarity scores between the normalization cohort and the enrolled vector as a normalization distribution. Or one can take the average of these two normalized scores on the left and right. And this is called the S norm or symmetric norm. So on top of that, I can make another enhancement. And this is called AS norm or adaptive S norm. So here, instead of using all of the scores between the test vector, I'm going to focus on the left-hand side. Instead of using all of the scores between the test vector and every vector in the normalization cohort, only a set of high scores are selected as a normalization distribution, meaning that it only takes into account those vectors in the normalization cohort that are similar to the test vector. And this can be done on the right-hand side between the normalization cohort and the enrolled vectors, so that only the high scores are selected for that normalization as well. So these are the common normalization methods used for single speaker verification. As I mentioned earlier, that the negative list detection can be reduced to multiple single speaker verification problems, so that each test vector can be compared or compute the similarity scores with each enrolled vector in the negative list. And that similarity score can be normalized separately for each vector, just like this. However, because the negative list is trying to determine whether a test vector matches any enrolled speaker using a single score threshold. So it would make sense to treat the scores with all enrolled speakers collectively as a single distribution. So that's why we propose this NL norm, which is unique for negative list detection. So here it still first finds the high scores in the normalization cohort with every enrolled speakers in the negative list. And then all of those high scores or the sets of high scores from all of the enrolled speakers are combined into a single set. And it's used to normalize S as a single distribution. So this has been found to improve the accuracy of the negative list detection. A second technique we have experimented with is to use a locality sensitive hashing, LSH, to reduce the number of PLDA similarity score computations. So it doesn't matter for which normalization method we use. For a negative list detection, first one needs to compute the similarity scores between the test vector and every one of the enrolled vectors in the negative list. On the other hand, only the high scores, meaning those are vectors in the negative list that are most similar to the test vectors, are relevant for negative list detections. So there's no point of us spending all of these computations on the low similarity scores and doing that accurately. And the same is true between the test vectors and the normalization cohort, because if you're going to use AS norm or NL norm, only the high scores are needed for the normalization. So to that end, LSH can be applied. LSH is an algorithm that hashes similar input items into the same bucket with high probability. So it can be used to quickly find a small set of nearest neighbor vectors that have the potential to produce high similarity scores with the test vector. So in this example, we're using LSH to find only 50, a set of 50 enrolled vectors out of many thousands in the negative list for the PLDA similarity score computation. And also only find a set of 200 vectors in the normalization cohort out of many thousands for the PLDA computation as well. So let's take a look at some result. Here is the result of on the open set and the open source MCE 2018 dataset. So in this dataset, there are 3,631 speakers in the negative list. And then here we're going to focus on two columns of the data. The first one is the EER, the equal error rate. That is a metric commonly used for this speaker recognition, and in this case, negative list detection. So it measures the error of the negative list detection. So the lower the rate, the better. And another set of data I want to look at is the time it takes to process a single test sample against the entire negative list. And that's shown in this the time column on the right. So for the baseline method, using PLDA only without score normalization, the EER for the test set is 6.49%. And it takes 864 milliseconds to process a single test sample. When adding a score normalization to it, in this case, we're using AS norm, the EER is reduced to 5.69%, but the processing time more than doubled to 1,975 milliseconds, close to 2 seconds. So that would be a large delay for real-time detection. So by applying LSH first to find a subset of the vectors in both the negative list and in the normalization cohort, and then we compute the PLDA similarity scores only on those subsets, following by AS norm. So this is the third row. We see that the EER is 5.66. It's very similar to the result without LSH, but now the processing time is reduced from almost 2 seconds down to 114 milliseconds. So on top of that, if we replace the normalization method from AS norm to the NL norm, then we see that the ER is reduced from 5.66% to 5.48%, with little change in the processing time. So here is a demonstrates that by using these two techniques that are specific to negative list detection. First, with the application of LSH, we can reduce the processing time drastically with little impact to the ER, to the detection accuracy. And then by using the score normalization method, NL norm, the ER can be reduced, meaning it's increasing the detection accuracy while keeping the processing time relatively low. So actually, that is the summary of this work. Let me just stop here, and I'm open to for questions.